All right, welcome back to The Explainer. Today we're diving into a genuinely fascinating paper titled Quantum Annealing with Symmetric Subspaces. Basically, a team of researchers from ASIT and Keio University over in Japan are tackling one of the absolute biggest hurdles in quantum computing right now. We're going to explore what looks like a major breakthrough in how we can solve incredibly complex problems without the whole quantum system just falling apart on us.
Now, this might sound completely backwards at first, but hear me out. What if the secret to building way better quantum computers isn't about giving them more space to think, but actually restricting their choices? I know, right? We usually assume more computing power means more freedom. But try to imagine quantum computing as navigating this vast, unbelievably complex maze. Sometimes, taking away the option to wander down every single random corridor is exactly what you need to actually find the exit.
Okay, let's unpack this a bit. As a quick refresher, quantum annealing, or QA, is our go-to technique for cracking those massive, mind-bending combinatorial optimization problems. We're talking prime factorization, training complex machine learning models, the whole post-quantum cryptography shebang. And the way it works is by mapping the exact solution of your problem to the exact lowest energy state of a quantum system. In physics, we call this the ground state. So, going back to our metaphor for a second, finding the ground state is basically like finding a hidden treasure sitting at the exact absolute center of our complex maze. If you find the ground state, boom, you've solved the problem.
So how does this actually play out in the physics? Well, it essentially breaks down into three main steps. Step 1, you start with what's called a drive Hamiltonian. You can kind of think of the Hamiltonian as the mathematical engine running our quantum system. We start this engine up in an easy-to-prepare ground state. Step 2, we adiabatically transition. That's just a fancy way of saying we slowly, and I mean very carefully, change the system over a period of time. We're actively navigating the maze. And finally, step 3, we reach the problem Hamiltonian. If we navigated slowly and carefully enough, the adiabatic theorem actually guarantees we'll arrive safely at the ground state of this new destination, handing us the solution to our massive calculation.
Sounds pretty perfect in theory, right? Just drive the system nice and slow and you get your answer. But here is the massive roadblock that is currently holding this entire technology back. What actually happens when the quantum state takes a wrong turn in the maze? Because in the real world, completely outside of perfect theoretical equations, the quantum state doesn't always stay smoothly on the path. And when it derails, well, your entire calculation is completely compromised.
The real culprits behind these wrong turns are what the researchers pinpoint as two main villains: non-adiabatic transitions and decoherence. Imagine you're walking through that maze we talked about, but suddenly the walls start shifting around you and the floor is literally vibrating. A non-adiabatic transition is when the system accidentally jumps out of the lowest energy state and up into a higher, excited state. Usually, this happens because the gap between those states was just too small, or the transition wasn't smooth enough. Decoherence, on the other hand, is the outside environment leaking in and scrambling all that delicate quantum information. Both of these things throw the system completely off track.
To really grasp the stakes here, the researchers laid out perfectly in their paper. They say it is difficult to prepare the exact ground state using QA with the existing technology. The imperfection of the ground state preparation induces a crucial error. And look, this isn't just some tiny negligible rounding error. If you're trying to simulate incredibly complex condensed matter physics or break down shortest vector problems for next-gen cryptography, falling into an excited state instead of the true ground state means your final measurement is just wrong. You've officially failed the maze.
So that brings us to the big fundamental question these researchers set out to answer. How on earth do we keep the quantum state from going off track? If the traditional method of just letting the quantum state wander through this massive space of possibilities is way too prone to errors and decoherence, what's our alternative? How do we fix the maze itself?
Well, here is the incredibly elegant solution they proposed, using symmetric subspaces to act as literal guardrails. It turns out, the researchers realized that a lot of the problem Hamiltonians we actually care about in physics already possess an inherent symmetry, meaning they commute with a conserved quantity, something like total magnetization, for example. So their big idea was, if we can lock our quantum system into a specific symmetrical lane, we can mathematically stop it from ever wandering into the completely irrelevant parts of the maze. So the crucial takeaway here is how this completely overhauls the engine of our system. The conventional scheme usually relies on a magnetic transverse field as the drive Hamiltonian, and that essentially forces the solution to be searched across the entire massive Hilbert space. It means every single possible path in the maze is wide open. But the new scheme proposed by the authors? They swap that out for a one-dimensional XY model featuring what's called a flip-flop interaction. Because this new drive Hamiltonian shares the exact same symmetry as the problem itself, the search is strictly restricted to a symmetric subspace. You are essentially blocking off like 90% of the wrong paths before the search even begins. It's brilliant.
Of course, a theory is really only as good as its proof, right? The researchers knew they had to put these mathematical guardrails to the test using rigorous numerical simulations, and importantly, simulations that include realistic decoherence. For their first big test, they chose the deformed spin star model. This is a highly relevant model to look at because it describes the dynamics of hybrid quantum systems. Think combining superconducting flux qubits with nitrogen vacancy centers in diamonds. Let's see how the guardrails held up.
And honestly, the difference is night and day. When you look at the energy spectrum using the conventional transverse field, you can see just how chaotic and incredibly jammed together those pathways, those energy levels can get. That clustering, that is exactly where non-adiabatic transitions happen. It's right where the system jumps the track. Now, contrast that with the author's XY model. By confining the system purely to that symmetric subspace, the relevant pathways are managed so much better. It fundamentally alters the landscape the quantum state has to traverse, keeping it safely shielded inside its specific sector.
Now, just to be absolutely sure this wasn't some one-off fluke with a specific problem, they ran a second major test using the random XXZ spin chain. This one is a notoriously complex model full of random interactions and an anisotropic parameter, but crucially, it still commutes with the total magnetization. They basically unleashed both the old conventional method and their new symmetric subspace method to try and find the ground state of this incredibly noisy random system.
The stark contrast in performance we're seeing here is just fascinating. We're tracking the estimation error, which is basically just how far off the final answer was from the true correct ground state, and plotting that against the total annealing time. Notice that dramatic, incredibly steep drop in the line representing the new XY model very early on. That dip right there represents the optimal annealing time, where the error is minimized way before environmental decoherence even has time to ruin the calculation.
Let's actually quantify what we're looking at, because it's huge. The estimation error for that random XYZ spin chain using the new XY model, it was roughly 10 times smaller than the conventional scheme. 10 times. That is an absolute massive leap in accuracy. And what's more, because that error hit its lowest point much earlier on the graph, the optimal annealing time is significantly shorter. So it's a massive double victory. You get a way more accurate answer and you get it faster. And faster means the system spends way less time exposed to the damaging effects of all that environmental noise.
So, let's pull all this together and look at the big picture for the future of QQA. This paper fundamentally proves three huge things. First up, the guardrails absolutely work. By using a drive Hamiltonian that inherently matches the symmetry of your problem, those pesky non-adiabatic transitions are severely suppressed. Second, shorter paths. Because the system isn't constantly getting lost in the weeds, the optimal annealing time is significantly reduced. And third, beating the noise. Spending less time navigating the maze simply means decoherence has way less time to step in and destroy your fragile quantum state.
It's honestly amazing to think about. By simply restricting a system's freedom to fail, we're actually unlocking its true computational power, and it leaves us with this really thrilling question to ponder. If actively restricting a quantum computer's choices makes it 10 times more accurate, what other complex mazes of the universe are we now equipped to solve? From designing entirely numerical materials to cracking completely impossible codes, the guardrails are finally up and the path forward is looking clearer than ever. Thank you so much for joining me on this explainer, and I'll catch you on the next one.